starting very shortly. What we've got to do today is we're going to do the precise definition of a limit. There are 3 questions, which I'm frantically trying to get to, and that I'm going to do with you, and show you essentially what you need to do to answer one of these types of questions. So I'm about ready. Yes, good. Okay, so I'm now zooming over to homework 2.4. There are only 3 questions. Let's see if you've been paying attention. Are you going to get questions in your test about precise definition of a limit?
No.
Will I give it in the final just because I want to?
No.
No. So this is going to be easy, right? As far as things go. Okay, this should be it. Here we go. What you should be looking at right now is question 1. Is that what you see?
Yeah.
Right. Now, and this picture has basically got all the structure to what the precise definition is. What you're looking at is a function called the square of x. There it is there. And you're being asked to find the number delta such that every value of x that has the property that it's x take away 4 is less than delta, that the square of x take away 2 is less than 0.4, right? You see the 2 on the y-axis, you see how it goes up 0.4 and down 0.4? That's what this bit is doing. So we're saying, can you get within 0.4 of the answer 2? So let's see what happens. Well, if you go along and down, there's a missing question mark here, right? And there's a missing question mark here. So when we're finished, we're going to have a number and it's going to go in there. And that's the end of it. So that's the question. I'm going to have to kind of show you where my numbers come from. It's quite visual. So that looks like that. That's your square root function. Right in the middle, you've got 4. Going along there, you've got 2. And then you had a number up here, which was 2.4. And you had a number down here, and it was 1.6. And there's a question mark here, and a question mark here. So what we're going to do first is we're going to find out what these 2 numbers are. And then from there, we're going to get delta. Delta is the distance from 4 to that, and it's a distance from 4 to that. And delta is the smaller of the 2. Okay, so let's see what I know. I know that y is the square root of x, and if y was 2.4, then can you see to get x, I just need to find out what 2.4 squared is. And on my calculator, 2.4 squared is 5.76. So, and I know this one. I'm not sure where to put it. 5.76. And from 4 to this end point is 1.76. So that's a candidate for delta. Now, if I look at the one on this side, the y value is 1.6, and I'm going to find what x value would give you that, which is essentially 1.6 squared. And if I go 1.6 and square it, I get 2.56. So on this side, I get 2.56. And the distance between here and here, right from here to here, is 1.44. And delta is the smaller of those 2. So delta is 1.44. And that is question 1 done. So according to yesterday, if you can get as close as you want to 2 and find a group of values of x near to 4 where that's true, then that means the limit is 2. And in this case, that distance from 2, we call that distance epsilon, happens to be 0.4. And when epsilon is 0.4, as long as you're within 1.44 of here, and delta is basically the distance from the middle to the outside, the shorter of the two, in this case 1.44, we have got it. So all we're being asked to do here is for one particular value of epsilon, figure out what the delta would need to be to make it work. And that's question one out of the way. Now, question two, I'm just going to draw the picture because it's easier than bouncing back and forward. Has a curve that looks like that. You don't even know what the curve's called, so it's just y equals f of x. Here you have a 1, and that's 1. You then have a 1.1 here, which gives you 0.8, and you have a 0.7 here, and that gives you a 1.2, and we are being asked to find delta. This one is even less work. Delta is the distance between here and here. On this side, it's 0.1. On this side, it is 0.3. Delta is always the smallest one. That's the end of question 2. So do you see in these precise definitions, you're not actually doing any formal proof. Aren't we just finding missing deltas to make certain things happen? What would the epsilon be in this question? Funny little e guy. What value would it be?
0.2.
Yeah. So what they've said is, if you make this 0.2, how big does delta need to be to make it work? And the answer is, as long as delta is 0.1 away from the middle, it'll work. And our last question. This might go down as the quickest math section you've ever done in your life. Last question. Picture looks like this. We have a y equals x squared. This guy is 1. That guy is 1. On this side, you have a 0.5 to a question mark. On this side up here, you have a 1.5 to another question mark. And don't be surprised about what you've been asked to find. Delta. Okay, let's go for it. You got 1 minute. Find out what the value of those 2 question marks are, and once you do that, you'll know what delta is. So you go for it. No pressure. 1 minute from now. Okay, I overshot the time, but hopefully that gave you time to finish if you haven't already. So let's see what we're going to do. Let's suppose I want this question mark on the left. Well, basically, I know that y is x squared, and I know that the y is 0.5. So it's going to be the positive square root of 0.5. So square root of 0.5. And the number I get is, oh, to 3 decimal places. Okay, that's good. So 0.707. I only need 3 decimal places. And on the other side, it's going to be the square root of 1.5. And the square root of 1.5 gives me 1.225. So the candidates for delta, well, if you go this way, 0.225. And if you go the other way, it's 0.293. So 0.225 is your final answer. Are we good with that? Delta is the distance from the center to each of the outsides, and it's the smaller of the two choices. And that is the end for this quarter of the precise definition of a limit.
So excuse me, does that mean that the limit from the right was more important than the limit from the left?
Well, it says here that the distance here is more important. I guess that's one way of phrasing it. We have to try and make sure that everybody works. So if I go the same distance either side, then I can guarantee as long as I pick values in that range, right, from here to here, everything will fit inside this. So in this case, yeah, I guess the one on the right was the one that was used because I thought it was more important. Sometimes you get lucky and the distance from the center is the same number, which means delta is that number. But sometimes one side is fat and the other side is skinny. And to be safe, you always pick the closer of the two, right? The small one. That guarantees that everybody in this little band stays inside this range. That's the whole trick. And then what essentially what the precise says is, yeah, I can shrink that down to anything I like, right? I could shrink that down to a billionth, right? But I can still find a little interval here where everybody in this little interval will be inside that 1 billionth range. And so the logic is you could shrink it to eternity, which means, yeah, the limit would be 2. It would eventually become, you know, whatever the limit happens to be in this case 2. So we are now starting a new section. I think it's 5, isn't it? Yes, it is. It's called continuity. So I'm going to start with the theory. What do we mean when a function is continuous? So the definition of a function being continuous is the following. A function is continuous at the point x equals a if the overall limit as x tends to a of f of x exists as a finite number. So what do I mean by that? I mean that the overall limit as x tends to a is a number. It's 4 or it's 24. It's not infinity, because can't you get an overall limit equal plus infinity, and you could get an overall limit equal negative infinity. So that's not allowed. So that's just the first part of the puzzle. A function is continuous at the point x equals a if this limit, this overall limit, exists as a single finite number, and that the limit as x tends to a of f of x is the same thing as the value of the function a. And you might think, well, wouldn't that just happen automatically? Well, not really. Now, what would that visually look like? It would look really boring. In fact, it wouldn't really look like anything was happening. Can you imagine this is a, and this fella over here is f of a. If a function is continuous, for want of a better description, isn't it just a boring piece of the curve where nothing happens? The curve just passes through the point the way it's meant to. In fact, isn't every single point that I'm doing my finger on, isn't every single one of them continuous? Right. So I think you might want to think of continuity, right, of a function being continuous is just a nice way of saying it's a nice smooth curve with nothing happening, right? Just a normal curve. And what's good about that is that if you have a normal, a function that's continuous at a point, then nothing really weird happens there, right? So what sometimes is much more interesting are when things are not continuous. Let's show you examples of a function not being continuous at a point x equals a. Now we have different phrases for that. You'll see it being called not continuous. And you also will see it in textbooks being called discontinuous. Those are the same thing, right? You can sometimes you'll say a function is not continuous at x equals 2, or you might say a function is discontinuous at x equals 2. They mean exactly the same thing. Robin, your dog is fascinated by something. What the heck is it staring at?
I think it's my monitor screen, but he's just anxious.
Oh, so he's learning calculus. A pretty clever dog you got there. Okay, so there are a number of different kinds of discontinuity. I guess I'll use that phrase, of a function being discontinuous. So let me show you some of them. This one is called a jump discontinuity. And let's just say at x equals a. Right, now it's not continuous, right? Can you see that the overall limit does not exist? So it fails under the first half of the definition. Would you agree that function does not have an overall limit? It doesn't exist. And that's it. And it's called a jump discontinuity. I kind of like the name. It kind of jumps from one branch to the other. Since we're in naming things. We very often call this piece the right branch of the function, and that's the left branch. It's quite a useful name. You know, if I want to say, look at the left branch, you're going to look over here, right? Correct. If I say, look at the right branch of this function, you see you're going to look over here. It's a name. So far, so good. Let's get myself set up here again. There we go. The next one that we're going to have a look at, in no particular order, is called a removable discontinuity. Here is an example of a removable discontinuity. Now, you might be looking at that guy and say, I don't see a problem with that. That looks quite nice. Well, it fails under the second restriction. Yes, the overall limit exists. Would you agree that I'll put a number in? Let's suppose that's 5. And this here, right, is at 2. Isn't the overall limit of this function 5? But isn't the value of the function at 8? 2. And you see, they're not the same. Now, if I picked that dot up and I stuck it where the hole is, wouldn't it now be continuous? So imagine I picked that up and I filled in the hole, it would be continuous, but it's not. And this would be called the right branch, and this would be called the left branch. Are we good? Any questions so far? I'm seeing whether they call it a vertical or an infinite discontinuity. I want to use the same terms that this textbook uses, if I can. You never find things when you want them. I'm still looking, and okay, I have 2 choices here. Do you want me to use infinite discontinuity, or do you want me to use vertical discontinuity?
Infinite.
Go for it. I'm going to call it infinite, and then I guarantee it'll be the other one, right? But at least I can blame Teresa for it. So the third major type of discontinuity is an infinite discontinuity. And you kind of sort of already know what it's going to be because of my little rant. They happen when vertical asymptotes are around. So let's suppose there's a vertical asymptote at A. And in this particular function, the vertical asymptote happens to look like this. Then we say there's a infinite discontinuity at x equals A. Why or how does that fail? Well, it fails here. Actually, it fails here as well. But doesn't the overall limit not exist as a finite number? The overall limit here is plus infinity, right? But that's not a finite number, right? It's not 42. So the 3 major types of discontinuity are, to remind you again, in no particular order, a jump discontinuity, which typically happens when you have a piecewise function. A removable discontinuity, they can happen with rational functions. It can be simplified, for instance. And good old-fashioned vertical asymptote situations, which almost always happen in rational functions as well. You can generate an infinite discontinuity. So I'm going to play about with each one of these and see what's happening. Right, so this is at x equals A. Is that still a jump discontinuity? Is that still a jump discontinuity?
Yeah, because even though the point's gone, there still wouldn't be connected together.
Sounds good to me. Agreed. Is it still a jump discontinuity? Yeah. You're not really fixing it by moving the dot around or taking it away, right? It can belong to either branch. It can belong to some place that's between them or above them or below them, or it can be totally missing, right? The value of f of a is where that solid dot is. In this case, f of a doesn't even exist. Here, the value of f of a is isn't the overall limit. You are gone. Right, here's a removable discontinuity. Is that still a removable discontinuity? Agreed? There is no f of a, doesn't exist. If I put the dot there or there, like I have here, still no good. Would you agree that the only way you could fix this would actually be to put f of a there? And now haven't you filled the gap? Which is why it's probably called a removable discontinuity, because really you could fix it, couldn't you? You could remove the problem and make it continuous again. I don't even think I need to do vertical asymptotes. Would you agree it don't matter how vertical you are, volcano, hole in the ground, or one of each, aren't you still going to be an infinite discontinuity? I think this went pretty good. Right? So what we're doing here is trying to formalize a little bit by giving names to places and functions that cause problems. Why are they important? You cannot find slopes of tangent lines if there's a discontinuity at a point, right? You can't find the slope of the tangent line. I mean, look at this guy here. Suppose that was x is 3. Suppose that a was 3. What is the tangent line? Well, is the tangent line the guy up here or is it over here? You know, there's no unique answer to that, right? If you're doing a vertical asymptote, you might say, well, I could do a tangent line. The tangent line is my pen. Okay. Well, I guess in one sense it is. But here's the problem. What's the slope of that?
0.
What? That's 0. What's that? Infinity. Infinity. Infinity is not a good answer, is it? It's not really a number, is it? So vertical asymptotes, you can't get tangent lines at the points where vertical asymptotes are. Can you get tangent lines anywhere else? Sure. I mean, would you agree I could get a tangent line here and I could get a tangent line there, but I can't get one at a discontinuity. So tangent lines don't exist at points on a graph that are discontinuous. So we spend a little bit of time recognizing that fact and being able to identify and in a way label them. And here is a totally non-scientific made up way of telling if you have a discontinuity. What I pretend is that the function is a road and I am driving along this road. If I get killed, it's got a discontinuity. So here goes. Dead. Right? Just fell in a hole in the ground. Dead. Just shot up to the moon. Dead. Right? So if you drive from left to right and you would get killed, you have a discontinuity. It can be a hole in the ground where you just disappear. It can be you shoot off into space and die of lack of oxygen, or some idiot decided to have a break in the road. So if I drive along here, won't I just kill myself because I'll leave the road and smash into a wall or something? So not a very scientific way, but it's a way of looking at a graph. So if there's a problem, if you get killed, you're probably looking at a discontinuity. So, oops. This might work. I tried putting my mouse over the thing and that annoying right hand. So I decided not to bother. And I don't know if I can zoom in, and it's probably not much, but I'll try. Right. We are looking at a very damaged function. There are quite a few discontinuities in this function, agreed? And we are going to look at them right now. We're just going to focus on where the discontinuities are and what kind they are. Not worrying about what these questions are. I'm just using this as graphs that we can do. So looking at this function, can you find any place where there's a discontinuity? And I'd like you to tell me what kind. Removable, jump, or infinite, okay? Somebody start the ball rolling. Give me a place where there's a discontinuity.
At -2, and it's a jump.
Agreed. Do you see the jump? At x equals -2. Give me another one.
-4, removable.
Agreed. Give me another one.
Or infinite.
Yeah, because this side here, I'm thinking that goes down forever. So I would go infinite. You could say it was jump as well, but I think it's more likely to be called infinite. Have we missed any?
There's
We good on that one? Say that number again.
x equals 2.
Yeah, agreed. We did miss that one. So right now, same question. We're not too worried about. Oh, well, actually, this question is exactly what we're doing. But in these questions, this question here, you only need to tell me the x coordinate of what's happening. I think it would have been better if you told me the x coordinate and what kind. But so let's pretend that's what the question was. Looking at that guy, can you see any discontinuities?
X equals -1.
Agree, infinite? Infinite discontinuity. Any others?
At x equals 1, you have a jump discontinuity.
Agreed. Anything else?
X equals 0, there's a jump discontinuity.
Right, and there's one more. I don't know if you can see it. It's very faint because this is a small picture.
X equals -2.
Yeah, what's going on there?
Removable.
Removable. Okay. Do you feel comfortable now that if you got one of these very damaged functions, that you would be able to identify the x coordinates of where the discontinuity is, and if you were being asked, you could even put a label on it and say it's a removable, it's a jump, or it's an infinite. Okay, so back to notes now. Now, I call them left and right continuous, so let's see what their phrase is. Let's find out, otherwise I'll just give them my name and go on. Okay, we're going to look at right continuous and left continuous. Sometimes called continuous on the right or continuous on the left. And so I think they're close enough that if I use this phrase and the book uses that, you know what I'm talking about, right? So what in the heck does that look like? Well, let's do a definition. A function is right continuous at a point x equals a if the limit as x tends to a plus of f of x exists and is a finite number. And that the limit as x tends to a plus of f of x is equal to f of a. Isn't that almost an exact, oops, bring this back up. Isn't that almost an exact carbon copy of the definition of just being continuous? They're side by side. What does that look like? Let me show you. I'm kind of doing overkill with the dot. Now, this is x equals a. Would you agree that x equals a, this has a jump discontinuity? You agree? Now, if you find the right-hand limit, right? This one coming in from the right-hand side. Right? This guy here has a right limit. Would you agree that the right limit is f of a? And isn't the value of the function the same? So when you are talking about a thing being right continuous, aren't you basically saying that the right-hand branch ends at the place where the function is? Right next door to this this function is not right continuous at x equals a. What's the problem? Isn't the value of the function where the dot not here? Okay, look at this one. Is this function right continuous at x equals a?
No.
What is it in fact continuous?
Left continuous?
It's left continuous. At the end of the branch, does the function live there? So this is left continuous. This is right continuous. And this isn't anything. Well, I guess it's a jump discontinuity, but it's not left or right. Visually, can you see a left and right continuous? When a function could be right continuous, when it could be left continuous. There is no need for it to be either of those two. As you get, it could simply just not be continuous at all. Do I need to write down a formal definition, or could you imagine that the limit as x tends to a minus exists and the limit as x tends to a minus is f of a? That would be the formal way you would describe a left continuous. So I'm now going to return back to a couple of these pictures that we did earlier. And we're not going to talk about is it continuous? We've done that. We're now going to talk about, is it left or right continuous? Okay. And I'm going to start at x equals -4. This function is a removable discontinuity, right? That's what it was and still is. This function is not right and it's not left continuous. What's the problem? Why isn't it either of those?
Because no point exists to connect it.
Yeah, there's no value for the function f of a. Okay. What about at x equals -2? Left or right continuous? It's one of those two. What is it at x equals -2?
Left.
Agreed. At x equals 2, left or right continuous?
Right.
Say that again.
Would it be right
At
continuous?
x, correct. I know this one we've decided, or at least I and a couple of you have decided this has basically got a vertical at infinite discontinuity. Don't care. At x equals 4, is it left or right continuous?
Right.
You see that little dot at the end there? That's where you go looking. If you are interested in left and right continuous, find out where that solid little dot is. Is it on the left branch or is it on the right branch? If it's on any of them, right? And if it exists, right, if it's there, you're probably going to have a left or a right.
So
Do
on
one
the-
more of it. Yes.
Something with that many branches, how would you define it as left and right? Or would you just
Well, localized at x equals 4, that's left and right. So you're looking at a value of x, and in that little part of the world, there's a left or a right. But I guess if you're looking, there's a left or right, and then this is a left, but that's a right. You know. So I only focus on one value, in which case I've got a left and a
so
right.
to answer a question like that, it would be set limits or parameters and then say this is the limit for this limit parameter.
Yeah, right. Suppose I was interested at -2, right? Do you see I would call this the left branch and that the right branch? And do you see in this case the left branch has it, so it's left continuous. Last example, and then we'll call it a day. This guy. Sneaky one. At x equals -3. I haven't talked about that. Left continuous or right continuous at x equals -3?
Is it
Right.
right because there's no left?
Well, yes, that's part of it. And isn't the dot right there? So you can still be at the ends, you know, functions that just suddenly finish. They can have left and right continuous sometimes, not always. Right, at x equals -2, there's a removable discontinuity. Would you agree? No left or right in that particular question. There is a vertical or infinite discontinuity at -1. Okay, let's talk about that one. Does x equal -1 have a left or a right continuous or nothing? What do you think?
Neither.
Neither, because there isn't a number, right? It has to have a value. Infinite doesn't count. Okay, what about it x equals 0? Left or right?
Left.
Agreed. There's the dot. Last one, at x equals 1. Left, right, or neither?
Neither.
Agreed. What's the problem? Why has it got neither? You're correct, it is the right answer. But what, how did you decide?
The value doesn't live on the line.
Yeah, do you see that little point which represents the value of the function? It's not on the left branch and it's not on the right branch. It doesn't live in either of them. And that makes it not left or right. Okay, we learned some, well, I hope we learned some interesting stuff today, very visual. Haven't done any questions, at least any homework questions, but we will get to do that tomorrow. And say hi and bye-bye.
Thank you.
You're
Thank
welcome.
you so much.
So
Thank you.
real quick,
You're welcome.
just to clarify,
Oops.
there are no,
Right, I think it's Izzy that's talking. Go for it, Izzy.
Sorry.
What's your question?
just to clarify, we won't be calculating tangent lines on functions that are discontinuous ever, or just this class?
You will not be calculating tangent lines on discontinuous functions. Ever in this class.
Okay, good, because
Ever. But there's always a qualification.
there's
to
always
that.
a but.
It is, there always a but. It is theoretically possible, even although we're not going to do it. It is theoretically possible that you can get a thing called a left tangent and a right tangent. Can you imagine a piecewise function that's split?
Mhm.
Can you get a tangent line on this piece and a totally different tangent line on that? And when you do that, they are called left tangents and right tangents. So you know how there's a left and a right for continuity, there's a left and a right for limits, there's a left and a right sometimes for derivatives, but we won't go there, right? It's not really very helpful to find those things. And if it's a vertical asymptote, the tangent line is a vertical line, so in a way it doesn't exist because it's not a finite number. So you don't need to worry about them ever.
Okay, cool. All right. That's all I wanted to find out, because I know that as we progress through college courses, they teach you one thing and then you get to the next class and they're like, by the way, we told you this, but it doesn't apply in this class. Rules are out the window. Okay, just wanted to make sure. Thank you.
Oh God, no, I am going to say to you things in this class. Remember we told you this? Well, actually, that's only half true.
But I just
So yes,